All right. Excuse me. Nothing like starting a live stream with a good throat clearing, right? So, welcome to class. Welcome to Monday lecture. I just wanted to start off by saying if you have emailed me over the past 4 days, I haven't had access to my email. I took my 3-year-old camping, which was exhausting but a blast. But anyways, I've been off the grid, which is why you haven't heard from me. But I wanted to let you know that you will absolutely get a response from me today. I have started working through my pile, the pile up that's in my inbox. Randall, hello and good afternoon, or good morning, I guess. It's still technically morning. So you will be hearing from me if you haven't already. I know I've replied to some people between Chem 305 and Chem 400. But anyways, I've been off the grid, but I'm back on now, and things will resume as normal. Off the grid is also our song of the day. You can hit that link in the comment section, as well as our whole playlist. I'm archiving all of our songs of the day as we move through the semester on Spotify. Good morning indeed. So anyways, you can follow along there if you like. Megan, hello and welcome. We're going to be talking about some chemistry today. So again, I mentioned that that kind of my perspective, my philosophy on the prerequisites for Chem 400 is Ni, hello and good morning. My philosophy on prerequisites are that any chemistry that you will need to know in this class, I will explicitly and directly teach it to you. That you're responsible for Sig Figs, unit conversions, and algebra. But that the chemistry will all come from me. So today's will probably feel like a bit of review. Certainly some elements, sorry, not to make a dad joke, will be familiar. But again, I'm going to cover all the chemistry science that you need to know. And you know, it's a nice way to ease into things. You're like, I remember the periodic table. You'll see. We'll get into it. Sorry, a couple things in the chat. Maury, good morning. Mason, hello. How's it going? Okay, Alexander, good morning. Noontime. Alexander, so Alexander has a question. Seif, hello and good morning. Alexander's question is: are we going back? Are we still going back on January 31st? Again, I haven't looked at my inbox yet, so I don't know if there's an email from the chancellor there waiting for me saying that we're extending things or whatever. So as far as I know, the plan is to go back, but my knowledge is 4 days stale. So I'll check the email, and you can rest assured that the second that there's a change that I'm alerted of it, I will pass that information instantly along to the class in the form of a Canvas update. So if things change, I'll post an announcement. But if we don't hear anything, then the assumption, the knock on wood thing that we're doing is back in person a week from today, which I so hope happens. So let's keep crossing our fingers and getting our booster shots. All right. So we actually get to start talking about science and chemistry a bit today, which is great fun. So, as Madeline, hello, Chad, how's it going? As you know, elements are defined by the number of protons present in their nucleus, and you can find all the information you need to know. Kendall, hello, about an atom on the periodic table. Now, this is kind of the one that I'm displaying right now is kind of a stripped down. Jamazenya, I hope I said that correct. Hello. Nargis, hello. This is kind of a stripped down version. This only has the atomic number for each element, but the periodic, Freya, hello and good morning. The periodic table that I'll be providing for you to use on the exam has a bit more information, and I'd like to highlight that for you I'm using everyone's favorite element, silicon. Let me just make sure my audio isn't out of whack. 1 2 1 2. Here I can bump it up just a little bit, but I don't want to create a feedback situation. Okay. So on the periodic table, you will have the elemental symbol. So the elemental symbol for silicon is Si, and there's my lecture notes. So this is right here, the elemental symbol. And one thing that I want to point out, elemental symbols are comprised of either 1 or 2 letters. And it's always something you should be aware of, that the elemental symbol is always capital. Oops. Dyslexia always makes teaching a little more exciting. It's capital letter followed by lowercase. All right. Now here's the thing. I'm not going to get super pedantic about it. For example, if you look at the element iridium. Iridium is IR. So you'll notice that I will write iridium with a capital I, and technically this is a capital R, but it's smaller, you'll notice. And I'm not going to, you're not going to lose any points on anything if you write a capital letter as the second letter, as long as it's smaller. But here's the thing, it must be smaller. And here's why. If it's not, things can get ambiguous. So for example, if you look at the element cesium, it's CS. This is cesium. If you do not make that second letter smaller and you write this is not cesium. This is carbon and sulfur. All right. So I'm not gonna. I had a professor one time who took off points for if you wrote a capital letter smaller. I don't care because it's clear. It clearly communicates. But if that second letter is not smaller and you write it the same size or a close size to the first letter, there you will, because the meaning is at risk. No one sees I, capital, tiny capital R, and wonders what this is. But everybody looking at this sees carbon sulfur. No one would see cesium. So that's the one thing you got to be aware of. If there's a second letter, make sure it's tiny to avoid confusion. All right, so back to periodic table. We've got our elemental symbol. Above the elemental symbol on the periodic table, there is a number, and this number is known as the atomic number. It's abbreviated with a capital Z, and the atomic number represents the number of protons in that element's nucleus. The number of protons in an element's nucleus is the defining feature for that element. So, so that is an important number. We'll be using it throughout the semester. Beneath the elemental symbol is another number. This is known as the atomic mass. And the atomic mass is the it is the mass of the element and the units presented on the periodic table. You'll notice all of the atomic masses are unitless. It'll just give you the number, but that's because they're all using the same units, and those units are AMU, which stand for atomic mass units. So even though the units aren't explicitly written, the mass atomic mass is always written across every element on the periodic table in units of AMU, so you'll want to include those when you're using it. And finally, the other thing that will be present in every cell of the periodic table I provide you is the name of the element. Many periodic tables don't include the name of the element. The periodic table that I provide for you, however, does. So you do not need to memorize any element names in this class. I'm not interested in your ability to emulate something like Wikipedia. I'm far more interested in testing your ability to think and problem solve. So I try to keep memorization to a minimum. There's a few things we can't get around, but you don't have to memorize any elements on the periodic table. I have a stepdaughter who is 13, and she's in middle school, 7th grade, and she had a chemistry unit. It wasn't like a full year long, but it was like part of the physical sciences curriculum, and she was talking to me about it, and she said that, oh my gosh, I hated the chemistry section. And I'm not gonna lie, it hurt my heart just a little bit. I died a little bit on the inside, but it was like, oh, why? What didn't you enjoy about it? I guess. And she was like, oh, we had to memorize like 20 element names, and that's why I hate chemistry. And I'm of the opinion that memorization just blows in general. So if you hate memorization, what's sad for me is now there's a conflagration of, turns out what she hates is memorization, but she thinks that chemistry is memorization, so it's gone down with that ship. I'm going to try to avoid that with you. You don't have to love chemistry at the end of this class. But I have to say, slight digression, a moment of personal pride was it was actually at FLC. I was teaching a Chem 400 class, and I was also teaching the lab class, and so I was checking pre-labs, and on the front of this one student's thing, it says chemistry is what it says in the front of the lab notebook, and underneath it, the student had wrote sucks. So chemistry sucks. I'm like, well, whatever. It's not everybody's cup of tea. But this is a moment of personal pride. Somewhere midway through the semester, they crossed out the sucks and wrote in is okay. And so I thought, if I can take a student from thinking chemistry sucks to chemistry is okay, that's mission accomplished in my book. Hope maybe there's some chemistry sucks people out there right now, and who knows, maybe your mind can be changed. I guess only time will tell. So this is the information of the periodic table: atomic number, elemental symbol, atomic mass, and name. Now we need to talk a little bit about isotopes. All right, isotopes. Starting with a definition. So the definition of an isotope. Isotopes are elements, or I should say, atoms of the same element with varying numbers of neutrons. All right, atoms of the same element with varying numbers of neutrons. And the way that an isotope is expressed is you need a couple things. First, you need the atomic number, right? You've got the atomic number, which is represented by the symbol Z, and Z equals the proton count in the nucleus. And then you have what's known as the mass number. And this is different than the atomic mass. All right, the mass number is represented with the symbol capital A, and the mass number is equal to the sum of the number of protons and the number of neutrons in the nucleus. All right, so if you take the difference between the mass number, if you take the mass number and subtract the atomic number, it will equal the number of neutrons in that isotope's nucleus. And that is how you use these two things to find the number of neutrons in the nucleus. Now, one of the things you'll notice is the mass number is missing from the periodic table. It's not present anywhere on the periodic table, so you have to be provided the mass number if you're talking about a specific isotope. All right, now, let's talk a little bit about isotopic nomenclature. There's a few different ways to use the mass number to explicitly state what isotope of an element you're dealing with, and these are the ways to do it. You can write the elemental symbol, which I'm just going to write as EL, with the mass number superscripted before the elemental symbol and the atomic number superscripted beneath. All right, so this is one way to express an element, an isotope. The second way is you could write the elemental symbol with a dash followed by the mass number. The third is you can write out the element's name, element dash mass number. So, for example, if you had an isotope of aluminum, which I believe, that's 13? Yeah. Aluminum and our mass number is 13, our atomic number is 13, and the mass number of this specific isotope of aluminum is 27. The three ways to write this isotope of aluminum is you could use the first method, AL, superscript the mass number, 27, subscript the atomic number. So this is one way to write aluminum 27. You could also write it as aluminum dash 27, or write out aluminum with a dash and a 27. So these would be the three ways to kind of use this isotopic nomenclature. Now, one thing you may notice about the two methods that I just said in orange, or underlined in orange, is that you might be going, well, wait a minute. I see that the mass number is present in both of them, but the atomic number is only present in the first one. So isn't that information missing? The answer is it's not, because every element always has the same atomic number. Every atom of the element aluminum will always have an atomic number for 13. And you can look up the atomic number on the periodic table. All right, so the atomic number is always on the periodic table, and you will always have a periodic table when you're taking exams. So if you were to be given aluminum 27 in either of these forms, and you were asked to find the number of neutrons, for example, what you'd have to do is find aluminum on the periodic table, realize that its atomic number is 13, and then take the difference. So this 13 is always available to you on the periodic table, and that's why it's dropped from these two ways of writing out an isotope's name. All right. Now, for my next example, for my next trick, I want to look at carbon. Now, carbon has three naturally occurring isotopes. All right, there are three naturally occurring isotopes of carbon. There's carbon-12, carbon-13, and carbon-14. All right. If I were to ask you how many protons were in the nucleus of carbon-12, you'd have to reference a periodic table. you'd find carbon, and right here, we find it on the periodic table. It has an atomic number of 6. So no matter what the isotope is, carbon has 6 protons in its nucleus. Which makes the difference between each of these isotopes, not the proton count, but the neutron count. Carbon-12 has 6 protons and 6 neutrons. That's why its mass number is 12, right? 6 plus 6. Carbon-13 has 7 neutrons in addition to its 6 protons, and carbon-14 has 8 neutrons, all right? That is the difference between the two. Now, if you look at the atomic mass of each isotope, carbon-12 has an atomic mass of 12.0000 AMU. Carbon-13 has an atomic mass of 13.0034 AMU. And, oops. Scoot this over a little bit. This is one thing that I do enjoy about teaching digitally that I'll have to adjust to when we move back to the classroom. No more lasso tool on a physical whiteboard. Carbon-14 has an atomic mass of 14.0034 AMU. Now, this is a little bit puzzling because if you look up the atomic mass of carbon on the periodic table, the periodic table presents you with one atomic mass. And you might be going, well, wait a minute. There's 3 different isotopes of carbon in nature. How do they present one mass? And your first thought might be, oh, maybe it's an average. It's not a bad thought. There's 3 different isotopes floating around in nature. Maybe what's presented on the periodic table is some sort of average of these 3. But if you look at the periodic table, the atomic mass of carbon is 12.01 AMU. Now, this is where things are a little confusing. You're like, wait a minute, that's almost exactly the atomic mass of carbon-12. If you took an average of 12.000, 13.0034, and 14.0034. Oh, wait, I think I made a mistake. Yeah, that last one is 0.00. Whoa. 32. If you take an average of this, the average is going to come out to be 13. So this atomic mass on the periodic table clearly isn't an average. So what is it? The answer is this is something known as a weighted average. When you learn to take an average, which is add the 3 things together and divide by the number of things. So add these 3, divide by 3. The assumption behind an average is each individual quantity is present in equal amounts. But they are not present, even though they all exist in nature, they're not present in equal amounts. Turns out of all the carbon atoms out there, 98.93% of all carbon atoms in nature are carbon-12 isotopes. 1.07% of them are carbon-13 isotopes, and 1 times 10 to the negative, this is so small I can't even see it. I need to zoom in on my notes. 10 to the negative 10th percent of all carbon atoms out there are carbon-14. A weighted average doesn't just look at the individual mass of each one, but it looks at the relative abundance. And so the reason why this number is so close to the mass of carbon-12 is because almost all carbon atoms out there are carbon-12. All right? And what I'm going to do for my first calculation is show you how to calculate, how to take a weighted average, how to take the isotopic masses and their percent abundances and calculate what the atomic mass would be on the periodic table, which is a weighted percent. All right, we've got a question from Willow. Are there only 3 isotopes for carbon, and if so, why? That is an excellent question. So these are the 3 isotopes of carbon that you find in nature. So if you go out into the universe, into, our planet and the rest of the galaxy, these are the 3 isotopes of carbon you're going to run into. That doesn't mean these are the only 3 isotopes of carbon. It turns out that there are a host of different synthetic isotopes that don't exist in nature that humans are capable of making, of building, of constructing. Now, when it comes to nuclear chemistry, which that's what this is, usually the synthetic isotopes are not very stable, which is why you don't find them in nature. Because when we do build these things, these kind of weird Frankenstein-esque abominations, they tend to fall apart. That doesn't mean they don't exist or have never existed, but it means that they're not stable enough to exist in the real world. And the answer to that question, that deeper answer to that question, if so, why? The simple answer, kind of on the surface, is the only isotopes we see in nature are the ones that are stable enough to stick together. And you can even judge, if you're to look at these percent abundances, you would say that carbon-12 is probably the most stable, since almost all carbon out there is carbon-12. We would say of these 3 isotopes that carbon-14 is very unstable. Look at that low percent abundance. When this exists in nature, it usually falls apart into carbon-12 or carbon-13. And we would say that this is pretty unstable. How is that for a non-committal qualification? Just because we find so little in nature. But it still is 1%. It's stable enough to hang out there in a severe minority of 1%, but still pretty unstable. It's decaying into carbon-12 as we speak, but not so fast that we can't observe it. Definitely there. And if so the simple answer to that question, Willow, of why is stability. Now, if your next question is, well, what makes an isotope stable or unstable? The answer to that question takes physics. Specifically, it takes something called chemical physics, which is a little bit beyond the scope of this course. I'd be more than happy to share what I know of it with you, maybe after lecture, or once we start meeting in person, we could get into it a little bit. But it takes more math than this course requires, so that's why we kind of got to stay at the surface level. But it's a fascinating subject. It's its own field of study, and it's this weird intersection between chemistry and physics. So if you like both of those things, digging deeper into that subject will definitely be interesting for you. What we are going to do right now is I'm going to show you how to calculate a weighted average to take the isotopic masses and the percent abundances and calculate what the atomic mass would be presented on the periodic table. All right, so the equation for calculating a weighted average, so if you want to calculate a weighted average, weighted average is going to be equal to, you have to take the first number times its percent abundance plus the second number times its percent abundance plus ... You do this for however many pieces of this pie you have, so you get to the nth number times its percent abundance. So you can take a weighted average of 2 things, of 3 things, of 8 things, right? However many things you have, you multiply each number by its percent abundance, and then take the sum. So to calculate the weighted average using carbon as an example with those isotopic masses, we have to take each... Actually, before we jump here, the one thing I want to mention has to do with these percentages. When you do this, if you're going to multiply a percent by a number, don't forget to convert each percent to a decimal before you multiply it by a real number. And to do so, if you don't remember how to convert a percent to a decimal, it's relatively straightforward. You take the percentage and divide it by 100. All right? So with that in mind, let's start calculating take our weighted average for the isotopic information we have on carbon. And before we do, I just want to give you guys the heads up. I don't normally explicitly say this is on the test, but it's beginning of the semester. I want to cue you in for this is the first thing you should really pay attention to. There will be one problem on the exam where I ask you to use the isotopic masses and the percent abundances to calculate a mass percent for an element on the periodic table. So this is going to be on lecture exam 1. So you definitely want to practice this situation. So let's do this for carbon. We have our first mass, which is 12.000 AMU. We're going to multiply this by its natural abundance as a decimal. That's 98.93 over 100. All right, we're going to do it for 003. I believe this was 0034. Yep. Take the mass of carbon 13, multiply by its percent abundance, and then do the same thing for carbon 14. All right, and its natural abundance was 1 times 10 to the negative 10th. And we have to put that over 100 as well. All right, I can't do any of this math in my head, so I'm going to bust out my calculator. One thing you should be aware of is if you are using a phone as a calculator, as I am right now, you cannot use a phone as a calculator on the exam, on an in-class exam, because you can Google stuff. So buy yourself a calculator, and I would recommend do all of your homework, do all of your practice stuff using that calculator so that you're familiar with it, so you're fast using it on the exam. Anyways, enough of that commercial. Let's crunch some numbers. So 12 times 98.93 divided by 100. My calculator is telling me that this is, my answer is 11.8716. Something you should be aware of. We have to apply the rules for Sig Figs as we go. You'll notice that 12.0000 has 6 significant figures, but our percent abundance only has 4. And when you multiply two numbers, you have to roll with the number that has less sig figs. So this product can only have 4 significant digits. I'm not rounding right now. You need to wait to round to the end of the problem, but I'm putting these 4 lines here to remind myself of the significant digits present in this product. Okay, we got a couple answers. Oh, let's see, Alexander, you're totally right. This is not 103. This is 107. That's my bad. Let's see. Freya. So the answer to your question is it could actually be any parts of the problem, but with this one, the presented information will be, or most typically, where is it? Here we go. Where I'll give you you're guaranteed to get this situation on the test. The isotopic masses and the percent abundances. So you get this and this, this and this, this and this, and I would ask you take a weighted average to calculate the atomic mass of this isotope. So Freya, that is what would be presented. And so now I'm taking that information and I am taking the weighted average, which starts by multiplying each mass by its natural abundance, and then we're going to add these all together. So let's take 13.034 times 1.07 divided by 100. This comes out to be 0.1394638. And again, I'm not going to round, but I need to keep track of my Sig Figs here. 13.0034 has 6 significant figures in it. My percentage has 3, so I can only keep 3 Sig Figs from this product. Okay, Freya, great question. So Freya said we don't count the denominator 100 as 1 Sig Fig. We are just using it to get the decimal. Yes, and Freya, the reason why we're not counting the 100 as far as Sig Figs go is because this right here, all of these 100s they're based on a definition, not a measurement. So if something's measured, it has Sig Figs, but that 100 is based on the definition of a percentage. The relationship of a percentage to a decimal is you divide the percentage by 100, then it equals the decimal. So that's not a measured number, it's defined as that relationship. So when something's based on a definition, it does not affect your Sig Figs. When something's based on a measurement, it does affect your Sig Figs. And that's why these numerators do, because the percent abundance is measured. And so that's why we're keeping track of them there. All right, let's take our last product, 14.0032 times 10 to the negative 10th divided by 100. This is going to equal, there we go. This is going to equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 4, 0, 0, 3, 2. Randall, let me double check, because maybe my math is off, maybe your math is off. Let's see. 13.0034 times, let's see, 13. Oh, no, you know what? You are correct, and I am off. This is 0.13913 13638, which I believe is what you said you got. 139. Yep. Great catch. Yeah. All right, now with this final one, let's look at our Sig Figs. Again, 14.0032 has 6 Sig Figs. But our percentage here only has 1 Sig Fig, so we can only keep 1 significant digit. Again, we're not rounding, but we are putting that line there so we can keep track of our significant figures as we go. All right, so let's add these all together. 11.8716 plus 0.1391368 plus 0.10 zeros 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 4, 0, 0, 3, 2. So this comes out to be 12.001073638014003 and 2. Chad, you will see that that it's actually not. It's actually not. You're gonna end up being okay, and here's why. So this is the correct value. Every answer in this class, there's 3 components to get it correct. Correct value, correct units, correct sig figs. Let's look at our sig figs. So with our first number, so we just did an addition. The last significant digit, oops, didn't want that to be so dark. The last significant digit is in the second decimal place. For our second number, the last significant digit is in the third decimal place. And for our third number, the last significant digit is in the 11th decimal place. And when you are adding numbers together, your answer must have the same precision as your least precise number. The least precise number is the number with its last significant digit that's the furthest to the left. So our least precise number is the 11.87. Which means our answer must have the same precision. So the last significant digit in our answer must be in the second decimal place. 0 is a number that rounds down. So our final answer will be 12.01. That's the correct answer with the correct sig figs. And AMU is the correct units. Freya, great question. Why don't we apply significant figures at the end? Here's the reason why you can't in this problem. Freya, is this problem as an example of mixed operations? So the thing that you're suggesting we can do, you can 100% do if you're just doing addition and subtraction the whole way through. Yeah. Because then you can. Or if you're just doing multiplication division, you can also apply the sig figs at the very end because it's the same rules. But because we start with a multiplication and then switch over to addition, that's why we have to do it each step of the way, because the rules for multiplication are different than the rules for addition. Okay, Randall, let's see. Would that small error cost me a point on the exam if I was slightly off? So yes, so the easy answer is you want to be as precise as possible on the exam, 100%. And again, remember, every correct answer is comprised of there's 3 components to every correct answer. The correct value will get you some points. The correct sig figs will get you some points, and the correct units will get you some points. And all 3 together get you full credit. In addition, and again, this is assuming that we're taking in-class exams because online exams are different, but the way I do my written exams in class is there's usually some partial credit along the way. So, you know, if you're off at the very end, but you've written out all your algebra and I can see that you had the correct steps and I can find where you made that mistake, you might get even more points because I can see, oh, all your method was right, but you just slipped this up here, or maybe you had a calculator error. So all that to say is the more work you show, the better chance you have at getting partial. If you just write a number and it's wrong, I'm giving you a 0. If you show all your math and I see that, oh, you understood what was happening, but you slipped up right here at this step, you're going to be able to score more points. So showing your work, I don't require it. You're not required to show your work, but the more work you show, the better chance you have at getting partial credit if your answer indeed is off. All right, so this is how you use molecular weights. Not molecular weight. This is how you use your isotopic masses and your percent abundance to calculate the atomic mass for an element. Chad, what I would do in that case, because funny story, my calculator couldn't handle that number either. It was too small. So what I had to do was this. Because my calculator wasn't driving with it either. So here's what I did. I looked at this and I thought 10 to the negative 10 divided by 100. This is 10 to the negative 12. So if I have 14.0032 times 10 to the negative 12, and I have to write that out in standard form, well then I need to take 14.0032 and move this decimal 12 spaces over. So I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I wrote in the zeros. And landed my decimal right there. So Chad, that's how I handled it because my calculator couldn't swing it either. But fortunately, I understand scientific notation and I know how to take a number in scientific notation, like 14.0032 times 10 to the negative 12. Oops, that makes it look like 4. And write that thing in standard form. So if your calculator can't swing it, hopefully your brain can. But that's how I had to do it because my calculator was like, nah, the number's too small. I don't care what it is. Turns out it didn't matter what it is once we applied the rules for Sig Figs, but you're not guaranteed to have that on every problem. Okay, so we're still kind of in the introduction portion. Your prerequisite class, you probably talked about isotopes, talked about the periodic table. We're going to talk about the periodic table a little more. Chad, all I can say is, let's see. I can tell you the exact calculator I would do. Well, maybe it's... this one. So any scientific calculator is going to be able to serve your needs in this class. I really like one called the TI-30XS. This is a great scientific calculator. If you have this calculator or a calculator like it, it will be able to serve all your needs. It doesn't have to be this one. This is just an inexpensive calculator that I really like. Oh, there's too many. I was about to drop the link, but there's too many characters, so I can't. Anyways, if you Google that calculator, it costs around like $12, $13, or any calculator like it. Any of the TI 30 series is going to be enough of a calculator to get you through. All right. So we're continuing with kind of our introduction to just some basic concepts and ideas from the prerequisite courses that you have taken that you need to be able to know coming into the class. But again, I'm taking the time to cover them. So for example, you probably talked about isotopes. You may not have calculated a weighted average or not. So it's some of the old with kind of a new Chem 400 twist on them. And we're going to spend a little bit of time talking about the periodic table. So there are a couple different ways that we can chop up the periodic table that you should be familiar with. I'm going to hang on. Okay. There we go. Okay. So I'm going to just expand this thing a little bit. So there are a couple different divisions of the periodic table that you should be familiar with. And the first one is the division between metals and nonmetals. So that dividing line starts right here. So if you look right here at boron and aluminum, that's kind of where this line starts. And it makes a little bit of a zigzag along down the periodic table. And these are the railroad tracks that divide metals from nonmetals. In addition, so you have right here all of your nonmetals are going to fall on this side of the line, with the one exception of there's one more nonmetal up in here, and that is hydrogen. So these are nonmetals. Let's just make that line distinct. So our nonmetals are all on this side of the railroad tracks. Hydrogen, hopefully, is not a hard one for you to remember because hydrogen's a gas. How could that be metallic? All right. The metals are found everywhere else. So all up in here. Including this little dude and these guys down here. All right, these are our metals. Oh. All right, so we've got this division. We've got the metalheads, which are pretty hardcore. We've got the non-metals, the kind of soft, folksy crowd. But then we have one more that kind of bridges the gap. And you can find them at the intersection of the metals and non-metals, kind of both sides of this railroad track. And you'll notice I'm not being very precise. That's because it's a little blurry. Everything close to this dividing line between the metals and the non-metals kind of have a little bit of both, have metallic qualities and non-metallic qualities. These are known as your metalloids. All right, your metalloids are those elements that kind of touch and are close to the dividing line between the metals and non-metals. So the non-metals, kind of soft, folksy music people. You've got your metalheads, that needs no explanation. Your metalloids are all those weird intersections, like your punks, your pop punks, like got some melodic sensibilities, but also kind of like their music a little harder. That's where they live. Those are the metalloids. So that's one thing. Given a periodic table, you should be able to identify your metals, your non-metals, and where those metalloids live. So this information that I'm presenting right here, this you could be tested on. This is stuff you need to know. All right, what I'm about to present next are a couple different ways of dividing up the periodic table that you won't be like this. I could explicitly test you on the exam. I could ask you a question. But the next material is stuff that I want to present. Yeah, boron is super emo. It's never content with its valence. It thinks it wants 8, but then it tries it. It's unhappy. It goes back down to 6. But it's unhappy there. It's just constantly whining, which is probably why I like it so much. Because I'm an emo kid who grew up, and now I have a job. But doesn't mean I don't like the music. All right, so that material you could totally be tested on. That'll totally be present on exam 1. This next stuff, I'm not going to explicitly test you on it, but I just more want to expose you to it, so you're familiar. All right. Another main division of the periodic table is right here. So you'll notice we kind of have these two kind of chunks of the periodic table that are the same level, and then there's this dip down. All right. The two sides of this. So this far left side and this far right side comprise what are known as the main group elements. All right, so these are the two halves of the main group of the periodic table. In contrast to the main group, you have this section in the center. These dudes right here are known as the transition metals. So you've got your main group, and then you have your transition metals. The main group has a reputation of being predictable, following a set of rules. The transition metals kind of thrash against that, and they are unpredictable, wildly interesting and unique and varied in their behavior, whereas the transition metals kind of fall into these set, predictable properties and reactivities. Transition metals are all over the place, and they're awesome, but it also makes them a little more complex. You'll notice that I didn't highlight this little island underneath either main group or transition metals. That's because these guys down here are not transition metals, and they're not main group elements either. They are known as the lanthanides and actinides. And we are probably going to talk about them the least. All right, those are the lanthanides and actinides. They're not main group elements, they're not transition metals. They don't do a whole lot, actually. They have some interesting engineering applications, but their reactivity is so uniform that they're almost all completely identical. It's an oversimplification. I'm offending lanthanide and actinide chemists across the world. I even happened to know one when I was an undergraduate. He's super cool, did very interesting things with them. He found a way of taking a relatively boring set of elements and doing interesting and unique chemistry with them. But that's for a different course. So they kind of all blend together. But I guess the exception proves the rule. You can find interesting and novel reactions with them, but more or less they're the same. Okay, the one last division, and again, you won't be tested on this. You won't be tested on this next one, but we will come back to it later in the semester and do a ton with it. The periodic table can be divided into groups. And the first group these are called blocks. So right here, the S block comprises everything in the first two columns of the periodic table, and helium. Helium applies or belongs to the S block. The P block can be found here. It is the other half of the main group, minus helium, of course. So this is the P block. The D block is also what we labeled earlier as our transition metals. So this is the D block. And then finally, the F block is comprised of our lanthanides and actinides. There we go. This is the F block. And again, You're not going to get tested on this now. We'll come back to it once we are talking about electron configurations. But I wanted to introduce this concept early here while we're talking about the periodic table. All right, now the last drop of coffee. I'm done with it now. The last bit of review, the last thing we have to talk about in chapter 2 is if you've, well, I was about to say if you've had a chemistry class. Everyone has. If you're here, you've had one. This is a topic that I know you have been exposed to. You may or may not remember it, and that's why I'm going over it, because it is that clutch. It is a small burrowing creature. We're not going to talk about that. We're going to talk about moles, specifically the mole as a quantity and a unit that we will be doing a lot of conversions with. If you're bored and looking for a good time, do a Google image search on something known as the star-nosed mole. If you've never seen one, it's like, imagine a small furry rodent with huge dig-in claws, but it has like a tentacle monster attached to its nose. It's gnarly. It's like something straight out of H.P. Lovecraft. So again, if you're bored and you're looking for a good time, Google image search star-nosed mole. You will not regret it. Unfortunately, our conversation is not nearly as interesting. It's a little more abstract, but let's go ahead and get this done. Let's rip this Band-Aid off. So what is a mole? Conceptually, a mole is similar to one pair. So if you have a pair of things, you have two things, right? A mole is similar to one dozen. If you have a dozen things, that means you have 12 of them, right? Yeah, Alexander, that is exactly where we're going. A mole is similar to a pair. A mole is similar to a dozen, but one mole is much larger. One mole is 6.022 times 10 to the 23rd things. And this is a number that's far and away beyond anything that we would run into or interact with in our daily lives. The one exception there is, I'm pretty sure, my wife has one mole of shoes in our closet. I haven't counted, so it could be off, but it's within a ballpark of an order of magnitude. I'm certain of it. You don't normally interact with a mole of a substance, right? I should say a mole of things, unless the things you're talking about are so dang small that you need a quantity that big. And something that is that dang small would be an atom, could be ions, photons of light molecules. Those things are so small that we need a quantity as large as a mole to describe the quantity, the number of things present. So with this knowledge, you can do examples like the following. All right. So for example, I could ask you, how many atoms are contained in a 3.2 mole sample of carbon? All right, now, this is simply a unit conversion problem. All right, you have been given that you have a 3.2 moles of carbon, and you want to know how many atoms. So we want to cancel our unit of moles, and we want to find how many atoms of carbon are present in that mole sample. Now, the ratio is on the previous slide that I just gave you. 1 mole of anything is 6.022 times 10 to the 23rd. So 1 mole of carbon has 6.022 times 10 to the 23rd atoms of carbon present. You'll notice that moles cancel, and now we got to crunch our numbers. So we have 3.2 times 6.022 times 10 to the 23rd. All right, my calculator is telling me that the correct value is 1.92704 times 10 to the 24th. All right, that's my correct value. But remember, only one finger visible. There we go. 3 things. There are 3 things that make an answer correct in this class. That is the correct value, which we've got here, the correct units, which are right here, atoms of carbon, and the correct Sig Figs. All right, so we need to figure out how many significant digits belong in this number. Our quantity of moles has 2 significant digits. Our quantity of atoms, our ratio, our conversion factor, this is a measured quantity. It's not based on a definition. So Avogadro's number has 4 sig figs. When you're multiplying, you have to roll with the fewer, whichever number had less number of sig figs. So 3.2 has 2. Avogadro's number has 4. We got to roll. Our answer has to have 2. So we count off our first 2 sig figs. 2 rounds down. So our final answer then will be 1.9 times 10 to the 24th atoms of carbon. And that is the number of atoms present in a 3.2 mole sample of carbon. Let's do another example. All right, let's say you have 1.30 times 10 to the 8th atoms of iron. So, Kendall, that is a great question. How do you tell the difference between a measured quantity and a definition? Definitions are things like unit conversions that are within a system. So if you're going from one metric unit to another metric unit, or one English unit to another English unit, that's defined, right? It's defined that there are 12 inches in a foot. Not because we found it out by measuring it, but that was the definition. An inch is so long, a foot is 12 of those strung together. A meter is so long, and a kilometer is 1,000 of those strung together. So if you're doing a unit conversion within the same system, that's a definition. Another definition that we used today was the definition of a percent. You can convert a percentage to a decimal by dividing by 100. That's a definition. Everything else, all data is measured. So for example, when I say that we have a 1.30 times 10 to the negative 8 atoms of iron in a sample, that's a measured quantity. We have no way of knowing exactly, but we took a measurement, and that measurement came with 1, 2, 3 sig figs. So all data, anything with units attached to it, is measured, unless you're talking about unit conversions within the same system. So that's a pretty good rule of thumb. Anything that's based on a definition is exact. Anything that isn't is a measured quantity. So in this, let me know if that makes sense. So in this example, we have 1.30 times 10 to the 8th atoms of iron in a sample. And we were asked to determine the moles of iron in this sample. All right, so here it's the exact same problem as we dealt with before, just in reverse. We have 1.30 times 10 to the 8th atoms of iron. And we want to convert from atoms to moles. And the conversion, as always, to go from atoms to moles or moles to atoms is 1 mole of iron has 6.022 times 10 to the 23rd atoms of iron present. Here atoms cancel, and now we have to crunch our numbers. All right, 0.30 times 10 to the 8th divided by 6.022 times 10 to the 23rd. So the value is going to be 2.15875124 times 10 to the negative 16th. Kendall, I see your question, and I will get to it in just 1 second. First, let's apply the rules for Sig Figs. 1.3 atoms has 3 Sig Figs in it. Avogadro's number has 4. So we need to have 3 Sig Figs in our final answer. 8 is a number that rounds up. So this will be 2.16 times 10 to the negative 16 moles of iron will be our answer here. Okay, Kendall, you asked a great question. So your question is, would the conversion between centimeters and inches, right, which is 2.54 centimeters to 1 inch, be a measured quantity or a definition? Excellent question. Anytime you're moving between units of measurement, so for example, centimeters is a metric unit, inches is an English unit, that relationship between those two systems of measurement is not based on a definition, it's measured. You get out a piece of string, you measure out how long 1 inch is, and then you put it against a ruler that has centimeters, and you use that ruler to measure what the equivalence is. So for a conversion between, those are measured. So all right, you've got to measure the relationship between different systems of measurement. And so those unit conversions are always measured. They're never defined. Great question, though. All right, now, talking about moles. I've got to be honest. The number of times, that ability to convert from moles to atoms and atoms to moles is incredibly useful, but it's somewhat limited. Um, okay, Mason, great question. So Mason just asked, for the prereq exam, do we need to memorize every unit conversion, or will some be provided? Kendall, you are so welcome. So, Mason, this is my policy. Um, So you do need to memorize the metric unit conversions. I won't provide those. Those are just so clutch that you just need to have them in your head. That being said, the English units aren't that important. So if you need English unit conversions or conversions to go from English to metric, I'll provide those for you. So don't cloud your mind. Don't waste your time on memorizing any English unit conversions. That being said, you do need to memorize the metric unit conversions. And if you open your textbook and you're overwhelmed by the number of metric unit conversions, you don't need to know all of them. In the last lecture, I went over which ones specifically you do need to know. So I would take a look at last lecture before I wrote out a table of the metric unit conversions that you need. Yeah, totally. Anytime. All right. So let's get down to it. We've got just a couple things left. So the main use, so we've been talking about moles, kind of introducing some stuff. But where this becomes super useful, actually, it comes into, it becomes super useful with respect to the atomic mass. So we said earlier, for example, you look up carbon on the periodic table, and it'll have a little 6 floating above it because carbon has 6 protons, and then underneath it is 12.01. And I said earlier today that the units here are units of AMU, and that is correct. That's atomic mass units. But atomic mass units, AMU, are crazy important because they have an alternate formulation. Turns out 1 AMU is equal to 1 gram per mole. The atomic mass units, the AMU, tells you the number of grams present in 1 mole of that, in a 1 mole sample of that substance. So for example, for carbon, the fact that carbon has an atomic mass of 12.01 AMU tells you that there are 12.01 grams of carbon in a 1 mole sample of carbon. All right, and you can write this ratio either way. You can also say that in a 1 mole sample of carbon, that there's 1 mole of carbon in a 12.01 gram sample of carbon. Both are useful because both allow us to move from mass, which is something you can measure by placing your sample on a scale in the laboratory, and you can use that to determine the moles, and you can use it to determine the number of atoms. So in our last 5 minutes, let's do an example. Determine the number of atoms in a 5.06 gram sample of copper. All right. Now, if I gave you the number of moles of copper that you were dealing with, you could use Avogadro's number to convert from moles to atoms. But I've given you grams, which means that we need a unit conversion that'll convert grams of copper into moles of copper. And the place that you find that unit conversion is on the periodic table. All right, so you go to the periodic table, you find copper. All right, copper has an atomic mass of 63.546. That means that there are 63.546 grams of copper in 1 mole. Grams of copper now cancel. Now we need to convert from moles of copper to atoms. And we know that 1 mole of copper has 6.022 times 10 to the 23rd atoms. So 5.06 divided by 63.546. Whoa, hang on. 5.06 divided by 63.546 times 6.022 times 10 to the 23rd. My value given to me by my calculator is 4.795159414 times 10 to the 22nd. Moles of copper have canceled. We need to look at our Sig Figs here. 5.06 has 3. Our atomic mass has 5, and Avogadro's number has 4. So we're going to be limited to 3 here. Counting off 1, 2, 3. This 5 is going to round our 9 up to a 10, which will round our 7 up to an 8. So this will be 4.8. We still need 3 Sig Figs though, so it's going to be 4.80 times 10 to the 22nd, and our units are atoms of copper. And that is our answer. All right, I have one more example. It's somewhat of a next level problem. I don't have time to work it, but here's what I'm going to do. I'm going to write it up here on the board. You take a crack at it over the next 48 hours, and when we return on Wednesday, this is what I'm going to lead in with lecture. This is going to be the first thing that I'm going to do. So, again, it's a little bit next level, but see if you can swing it. Oops. How many molecules of water are contained in a 1.000 milliliter sample? Notes. The density of water is 1.008 grams per milliliter. All right, this example is a little bit on the next level. Take a shot, see if you can do it. We'll come back on Wednesday and pick up right here. Thanks for everybody for hanging out. We had some awesome questions. I appreciate seeing all your bright and digital faces this afternoon. And I can't wait to continue our discussion of chemistry on Wednesday. And again, if you've emailed me, you'll have a response